Our main purpose in today's lesson is to look at the what we mean by rational exponents. Now, the word rational here is referring to rational numbers, and again, you should know what that means. It's anytime you see the word rational in mathematics, it is a synonym for fraction. That is, we could just as easily have said we wanted to talk today about fractional exponents. That is, we want to look at what does it mean to put in the exponent position of a power a fraction. Let's just look at some examples of what it is we're about to study and see just what they look like. Okay, so a rational power, for instance, we want this to have meaning. 4 raised to the 3/2 power. Notice how I said that. 4 raised to the 3/2 power. Or you could say the 3/2 power of 4. The 3/2 power of 4. Just a reminder, remember what we call the number that we're raising to the power, we call that the base, and I'll be using this terminology throughout, so I want you to be familiar with it. And of course, 3/2 here is called the exponent. And at times, you'll hear people refer to this whole thing as the 3/2 power of 4. So the whole thing's a power. The whole expression here is we're talking about as a power. Let's look at a couple more examples. Say, for instance, something like this. How would we read that? Well, now I've got a negative number down here as my base, so I just say negative 24 raised to the 2/3 power. Or again, you could say it the other way around as I've said it here, the 2/3 power of a negative 24. These parentheses are always appropriate. I could have even used them here. I could have written, you can always use parentheses, and outside the parentheses put your exponent. Inside the parentheses you put your base. How about, well, let's use a variable base. B raised to the 1.35. Is that a rational power? Yeah, because this is a rational number. Any rational number, we want to be able to legitimately put it in the exponent position, and this have a meaning. Will be meaningful. B to the 1.35, or the 1 35/100 power of B. One more. How about X raised to, how about a negative 2/5 power? Sure, negative 2/5 is a rational number, so we want this to have meaning as well. Okay, so now we know what we're interested in and what they look like. What do we want to? How do we want to define them eventually? But before we even do that, let's look at if we knew that they existed and we knew what they were, then what could we do with them already knowing the laws of exponents as we do? So let's look at just a couple examples of, given that we have these expressions, these rational powers, what do the laws of exponents suggest that we could do with them? So here we have a few examples. Remember the first law of exponents. When you have a power, or rather a product of powers of A, well, that's what we have here. If this eventually has meaning, and it will. 4 raised to the 2/3 power times 4 raised to the 3/4 power, that's a product of powers of 4. And the first law of exponents says that what we should be able to do is to find that power by simply taking the power of 4 we get by adding those exponents together. Nothing's going to change. We're going to do exactly that same thing as we did with integers and natural numbers as exponents. So this, because of the first law of exponents, has got to be the product of these two powers of 4. And then we just do the arithmetic of adding 2/3 plus 3/4. Well, that need a common denominator of 12, and so 3 will go into 12 4 times. 4 times 2 is 8, and 3 will go into 12. 4 will go into 12 3 times, and 3 times 3 is 9, and so we get 4 to the 17/12. How about the second one here? Well, now we've got a quotient of powers of A. And that's exactly what we have over here. These are powers of 9. And it's a quotient. It's a fraction. We're dividing two powers of 9. And what does the second law of exponents say? It says that you subtract those exponents. So this better be equal to 9 to the 2 minus 1/4. And then it's just ordinary arithmetic. Change that 2 to fourths. Well, that 2 is 8/4, so you have 8/4 minus 1/4 is 9 to the 7/4. Third example down here is power of a product. Power of a product is the product of the powers. I see a little mistake here. I'll just correct it. AB raised to the nth power is a to the nth times b to the nth, isn't it? And that's what we have over here. That's a product, and it's raised to a power. The power n here happens to be this negative rational number. And what this property says I can do is raise each one of those factors to that negative exponent. I'm just going to go to that step and stop here. I just want to illustrate what it is we will be able to do and already can do, assuming that we know that these will eventually be defined. One more example of using the laws of exponents in rational powers that we're going to define kind of suggests how we might end up defining this thing. Let's take, for instance, 17 to the 1/3 power. Now, eventually, that's got to have meaning. Well, one of the laws of exponents might even suggest what meaning it has. Remember the law of exponents that deals with a power of a power. If you have a to the m raised to the nth power, we know that has to be a to the m times n as a power. So if this is a power of 17, just happens to be a rational power of 17. If I take that as my base and raise it to a power, then that has to have meaning as well. And let's do it for a particular exponent. What if I were to take the third power of this rational power of 17? And according to this law of exponents, that must equal to 17 to the 1/3 times 3. And of course, 1/3 times 3 is 1, and which is 17. So without even knowing what this number is here, I know what its cube is. I may not know what 17 to the 1/3 is, but I sure know what it is, what I get if I cube it. I get 17. So let's see if we can't define, first of all, what we mean by b raised to the 1/nth power. Here's what we're going to say. We're going to call b to the 1/n the unique real number such that if the nth power of that number turns out to be b. That is, we want this expression right here, b to the 1/n, to be the unique real number such that its nth power is b. The unique real number such that the nth power of b to the 1/n is b. And we just saw an example of what we're saying here. 17 to the 1/3 is going to be the unique real number such that the third power of that number gives me the base. In this case, 17. Isn't that what it's saying? That this is the nth power of this will give you the base. Change the base to anything else. Say 25. And let's change that to 1/7. Then 25 to the 1/7 power is the unique real number such that if I take the 7th power of that number, I will get the base 25. Two questions come to mind that we have to consider. First, will b to the 1/n always be a real number? And secondly, if b to the 1/n is a real number, can we assume it's unique? That is, maybe there's more than one possible number that would satisfy this statement. So we got two things to worry about. Is there always an answer? Is there such a real number for this statement to be true? And then, is there only one real number for this statement to be true? Well, unfortunately, the answer is no to both questions. B to the 1/n is not necessarily a real number. It's not necessarily defined, and b to the 1/n is not necessarily unique. So we've got to look at under what circumstances this occurs. Easiest to see that again just by looking at a couple of examples. Let's take, for instance, this. Take -4 raised to the 1/2 power, the 1/2 power of a -4. We want that to be the number whose, in this case, second power is this base. That is, we want this statement would have to be true. The second power of this number should be a -4. Well, just take this much of it. The second power of anything, is it possible for it to be a negative? Not if it's a real number. If you put a real number in here and raise it to the second power, you're not going to get a negative. Right? Because a positive times a positive, it's got to be a positive, and a negative times a negative has got to be a positive, and here you're squaring the same number. There's not any way it could be negative. So this can't happen. There's no way this can happen, and so there's no way this can happen, or in other words, there's no way for this to be real. This is not real. Second question, is it unique? Again, by example, we can see that's not necessarily the case. 16 to the 1/4 is got to be a real number, the real number, whose fourth power is 16. Fourth power is going to be 16. The number we put in here, this needs to stand for the number that you raise to the fourth power to get 16. Well, you know there are two numbers you can do that with. 2 raised to the fourth power will give you 16, and -2 raised to the fourth power will give you 16. And we don't want a situation where we have some expression that can have two different values, because then you've got a possibility of an ambiguous statement. So we've got to set it so that this is unique when it's defined. So what do we do in this case, or these two cases? Notice that both of them, n is even. So we can deal with these both in the situation where n is even. When n is even, we don't want this to happen. We don't want a base that's negative. So we must assume that b, our bases, are bigger than 0. So we won't have this happen, because that won't be a real number if you have an even n and a negative base. And in the second situation, we've got two possible numbers whose power, nth power, will turn out to have that base. We've got to select one of them. Well, we're always going to select, in this case, when n is even, we're always going to choose b to the 1 over n to be positive, to be the positive one. So 16 to the 1/4 here is equal to 2, not -2. So we make, when n is even, we make these two restrictions. We choose positive bases, and we always choose b to the 1 over n to be positive. And in the case where n is odd, everything works fine. B can be any real number, and b to the 1 over n will be unique. So we now have a handle, so to speak, on at least this rational power, b raised to the 1 over n, where n here, again, is still restricted to being a positive integer. Now, just briefly, before we go on, a word on terminology here. I've been saying reading b to the 1 over n, either by saying it that way or reading it as the 1/nth power of b. But there's a third way that you can read that expression. Let's look on the pad here a second. Here are the two we've been saying. b with 1 over n as the exponent, we just read it b raised to the 1 over nth power, or the 1/nth power of b. But a third way can be to read it this way. We refer to 1 over n here as the nth root. So we read that right there as the nth root. Or some people just think of the n, the denominator, as being the root. And we read this then the nth root of b. So all three of these phrases represent this same number, b to the 1 over n. So we have this quantity, b to the 1 over n, defined, and we know how to read it and to interpret it. By the way, there's another term you'll see in some textbooks, or your instructor may use, in referring to this nth root, and they may say the principal nth root of b. And again, that's emphasizing, when we use that term, we're saying that it's unique, real number, and that it has, we've had the restrictions on b and n so that it is unique and a real number. So when someone says, what's 4 to the 1/2 power, then you know that they're talking about 2. 4 to the 1/2 power. The principal second root of 4 is 2. There's two numbers you can square, whose square will give you 4. But the principal square root of 4 has been defined to be 2. And so that we're all in agreement and we all get the same answer that way. Now, here's another way to phrase it. Look over at the pad. This may or may not be helpful to you, but I kind of throw it out at you, and if you find it helpful, great. The principal nth root of b. I'm using parentheses here for the word of. So this is read, principal nth root of b. That's what this notation right here is. B to the 1 over n is equal to some number a. So I'm introducing another symbol here to represent this thing we're calling the nth root of b. And that's equivalent to, that's this little symbol right here you can read is the same as or is equivalent to So b to the 1 over n equals a is equivalent to saying that a is that unique number that you can raise to the nth power and get b. So anytime you have a root statement like this, you can change it into a power statement like this, because this is the nth power of a will give me b. And again, there's that warning, negative bases with even roots. Remember, that's the restriction we have to watch out for. Those aren't real. And then also in even roots, we always take the principal or the positive in that case, the principal nth root is the positive choice. So now what about other rational exponents other than just 1 over n? For instance, 3/2, 2/3, and so forth. It's really a very natural consequence of the laws of exponents that we define the rest of the rational exponents once we know and have defined what we mean by b to the 1 over n. We'll take a few examples to see how that works. Let's start with a fairly routine one. Let's take 4 to the 3/2 power. And what we're going to use is the law of exponents of the power of a power. A to the m raised to the nth power is a to the m times n. Well, and I'm going to use it going this direction. That is, I'm going to think of this as a product of two exponents. Well, it is. I can write it as 1/2 times 3. And now this property says that I can take that power and write it as a power of a power. So if I write it as 4 to the 1/2 cubed, there's a to the m raised to the nth power, just as this is. But this, we know, is the principal square root of 4. And we know the principal square root of 4, or the positive square root of 4, to be 2. And 2 cubed is 8. How about 27 to the 4/3? 27 to the 4/3 power. Well, again, I'm going to think of that as a product, the exponent 1/3 times 4, and then using this property of exponents, I can write that as a power of a power, and 27 to the 1/3 power, the principal third root or the cube root of 27, or again, the real number that you have to cube to get 27 is 3. I can substitute this right here for 3, and 3 to the 4th, we know, is 81. In other words, in general, if I have some base b raised to a rational exponent m over n, one of the ways that I can calculate that rational power is to rewrite it using this law of exponents as b to the 1 over n quantity raised to the mth power. And if this is defined, if this thing right here, this base sitting in here, is a real number by the restrictions that we have discussed, then this will be a real number, b to the m over n. There is a second way that you can write this, because of the commutativity of multiplication. I could just as easily have said up here 4 times 1/3 and change the order here of these powers, and I think it's easy to see that what you would get down here in the general case is b to the m raised to the 1 over n. And again, both of those two statements should be true, but in practical circumstances, you're probably going to do it in this order when you're doing calculations with the numbers, just because it's easier to do the multiplication. I mean, imagine up here in this case, had I done it the other way around, I would be taking the 4th power 27 and then trying to find the third root, which would be a little more of a chore if I'm doing it by hand. So next, I guess we should look at some exercises involving this. Well, in the exercises, there are basically two things you're going to be asked to do with rational exponents. One is to evaluate them, which we've done a few already. We'll look at a few more before we go on. And then the second thing that you'll be asked to do is to simplify expressions involving rational exponents. So evaluate, what does that mean? It means find a value. You're to actually come up with a value from the exponential expression. And to simplify just means to make it put it in a simpler form. We'll be more specific about that when we'll look at those. But let's begin by again just looking at a few more rational powers to evaluate. If you look at the pad, it says evaluate the following rational powers, if possible. Again, I just threw in a warning here. Keep in mind this negative bases with even roots are not real numbers. And just to confuse the matter a little bit, maybe, I threw in on number 1 here a whole bunch that look a whole lot the same. But I think we can recognize the difference here. 36 to the 1/2 power, or the second root, or the square root of 36, the unique positive real number whose square is 36. Everybody should say 6. Now what about that? Negative bases with even roots? Certainly an even root, but not a negative base. This base is not negative. What we're looking at is the negative of the first one. It's saying here the negative of 36 to the 1/2 power. And of course, if you know that first one is 6, then this must be negative 6. How about the third one? Well, now we got a negative base, don't we? Negative base and an even root. A negative base and an even root is not a real number. And that's what we say. Not real. Or your instructor may ask you to write that it's undefined, because that's also true. It is undefined. We certainly don't know what it is. We have not defined it. So you may be asked to say it's undefined or that it's not a real number. 36 to the negative 1/2 power. Oh, negative exponent? Oh, well, sure. We know what to do with negative exponents. We write them as 1 over that base raised to the opposite. So that would be a positive 1/2. And we just calculated that. 36 to the 1/2 power 6. So this must be 1/6. And finally, this last one's got a negative sign just about every place possible. How you read that? It says the negative of a negative 36 raised to the negative 1/2 power. Well, definitely we have a negative base. But we have a negative exponent here, which might be a little confusing. So, it might be worth making at least one try at evaluating this by doing the same thing we did it previously, and that's getting rid of the negative exponent, which we can do, because we can put that base, which is negative 36, in the denominator, raised to the negative of that, which would be 1/2. And notice, everything moved. That actually didn't. It's still up there, but it doesn't really matter. What we have sitting down here is not a real number. Negative base with an even root is not a real number. This is not a real number, so the whole thing is not real. Okay. Let's see what the next group look like. Well, a little more same base, sort of, but now we've got it raised to a rational number 3/2 power. Well, let's go look through these. It's 36 to the 3/2 power. Well, we said what we would do is write that as the root. There's the root of 36, the square root of 36 cubed, and work it inside out. The principal or positive square root of 36, well, we just did it, is 6. So I can replace inside the parentheses with 6. And then 6 cubed, you might have to stop and figure that, but it is 216. And what about the next one? Well, there's a negative, that's a negative sign there. Here's a negative 36 raised to the 3/2 power. Again, it's like that one. That is not a negative base. That's the negative of what we just did. That's the negative of, let me put a little dotted line here, separate this. That's the negative of 36 to the 3/2 power. And we just did 36 to the 3/2 power. So the negative of that must be, taking advantage of the fact that we did it right here, must be a negative 216. Yeah, another dotted line might clarify things a little. What about the next one? Well, keep in mind, when you see a negative base, a little light ought to go off, a little bell or something. Negative bases, yep, negative base, even root. And now, it becomes kind of important to recognize where the root is. The denominator of a rational exponent is your root. The numerator, you might say, is your power. The root is the denominator, the numerator is the power. So this is second root with a negative base. I can stop right there and say not real. Doesn't matter what that power is going to be up there, it's going to yield me here a unreal quantity. The next one, 36 to the negative 3/2 power. Well, again, I got a negative exponent, so I can write that as 1 over 36 to the 3/2. But I know what 36 to the 3/2 is. It's 216, so this must be 1 over 216. And the last one, there's that negative base again. Even though there's a negative out here, that negative base, and if I take it in and move it into the denominator, it'll still be a negative base. It'll still have an even root. So this one is also not real. The next group down here have a little different bases. Let's take a look at those. Number 3, negative 16 to the 3/2 power. Again, a casual observer might read that as a negative base, but we know it isn't. It's the negative of 16 to the 1/2 power cubed. You can just write it like that. And the principal second root of 16 is not 8. It's the number you have to square to get 16. That's 4, right? So inside there you put a 4. Now what do you do first? Always exponent first. Cube that. 4 cubed is 64. Then take its negative. Comes out with a negative 64. Number 4, looking at, a negative base. But it's an odd root, so that's okay. The negative 27 raised to the 1/3 power, or the cube root of a negative 27. We're looking for the real number that you cube to get a negative 27. It's got to be negative, doesn't it? And negative 3. Again, if you're not sure, you can always check yourself afterwards. If that's the number you cube to get the base. And it is. Number 5, well, now we can take advantage of knowing that. Here we've got a rational exponent with a power of 4. Well, again, we're going to change that into a root, then a power. And we know that the root, or the third root of a negative 27, we just calculated as a negative 3. If you raise that to the 4th power, well, you raise any number to an even power, it's going to be positive, and this one's going to be a positive 81. So now the last one in this group, 27 to the negative 4/3. Well, we got a negative exponent, so we'll first write that as 1 over 27 to the positive 4/3. And now we know that is 27 to the 1/3 raised to the 4th power. And the cube root of 27 is 3. So we have 1 over 3 to the 4th, or 1 over 81. In case you can't read them, that's negative 16 to the 1/4. That's the quantity negative 16 raised to the 1/4. That's a negative of 16 to the 5/4. And that's the negative of 16 to the negative 2/4. So pause the tape, try those, and then we'll continue. Okay, so if you finished, let's look at these 4. Well, again, your first glance, a man on the street might just look at that and think it's undefined, or it's not a real number, but again, we know that's the negative of, if you wanted to emphasize it, 16 to the 1/4. And the principal 4th root of 16 is positive 2. So this is a negative of positive 2, or negative 2. Number 8, however, you got a negative base, even root, so this is not real. Number 9, again, it's a negative number. It's the negative of the 1/4 root of 16 raised to the 5th power. And the 16th raised to the 1/4 is 2 again. And raise that to the 5th power, and you get a negative 32. And then finally, number 10 is a little maybe tricky. Watch it over there. Look what we've got. We've got a negative 2/4. Well, remember what we said? When we deal with rational exponents, we're always going to reduce them. So we would write that as a negative 1/2 power. And so that can be changed then to a negative 1 over 16 to the 1/2 power. Notice again that negative 1 actually stays in the numerator. And 16 to the 1/2 power is 4, or a negative 1/4. You always want to reduce these rational exponents to lowest possible factors, you can, because otherwise you can get confusing results. So we always make the assumption that they're reduced to lowest terms. Now, what about some where the bases are fractions? Again, it's just a consequence of the laws of exponents, the way we would handle something like this. Well, turns out though, with this fractional base, we also have not only a fractional exponent, but a negative fractional exponent, don't we? So let's do this one maybe the way, kind of how we did before. Fractional exponent, we know what that, a negative exponent, excuse me, we know that means that we're going to take that base, 4/9, and raise it to the negative of that exponent in the denominator. And now I'm just going to use the laws of exponents. This is a power of a fraction, and I know a power of a fraction, I raise both numerator and denominator to that exponent. So this would be 1 over 4 to the 3/2 over 9 to the 3/2. Make this one a little bit bigger, emphasize. And now evaluate those. Well, 4 to the 3/2, we did that a moment ago, is 4 to the 1/2 cubed. So 4 to the 1/2 cubed, that's 8. And 9 to the 3/2, maybe we ought to write that one out, that's 9 to the 1/2 cubed. Oops, there we go. And the 1/2 power of 9 is 3, and 3 cubed is 27. So this is 1 over 8 27ths. But of course we're not going to leave it like that. That's a complex fraction. And so if you invert and multiply, or actually you're dividing this, right? You're dividing 1 by 8 27ths, you'll get 27/8. Well, that's kind of a long, tedious way to do this. There is a nicer way to approach when you have a fraction raised to a negative exponent, and you may have seen that it's kind of an additional property of exponents, and maybe I'll show that to you first, then we'll do another one. Let's just look at on another sheet here a second. A over B raised to the negative nth power. Let's stop from using negative exponents or using fractional exponents for a minute. And you might recall that a way to simplify that, besides writing it as 1 over A over B to the nth power, is to take the reciprocal of the base and change the exponent to n. And that always is the result of doing this, taking the definition of a negative exponent. So let's do the second one in our exercises in that manner. Number 18, there we have 64/27 raised to the negative 4/3. Whole lot easier way to do it. Take the reciprocal of the base raised to the negative of the exponent. And so that'd be a positive 4/3. Positive 4/3. And now we do the same thing we did before, use the laws of exponents. That's 27 to the 4/3 over 64 to the 4/3. And now take each one of those and evaluate them. The third root, do your root first, and you probably do this in your head. The third root of 27 is 3 raised to the 4th power. The third root of 64 is 4 raised to the 4th power. Or 3 to the 4th, that's 81, over 4 to the 4th, 4 to the 4th, or that's 16 squared, is 256. Well, one more, and let's do that the same way. 16 over 625 raised to the negative 3/4. We're going to take the reciprocal of the base and the negative of the exponent. So that would be positive 3/4. A over b to the negative n is b over a to the n. That's what we did. And now, you might be able to handle it this way as well. Take 625 over 16, and let's take its 4th root, and then cube that. Isn't that the same thing? There is b to the 1 over n raised to the nth power. Well, the 4th root of 16, that's easy. That's 2. Now the 4th root of 625 is, well, 625 is 25 squared, or 5 to the 4th power. So, yeah, the number that you've got to raise to the 4th power to get 625 is 5. And now cube that. And the cube of a fraction, you just cube both numerator and denominator. That'd be 125 over 8. Now we want to simplify some expressions involving rational exponents and variables as their bases. Let's look at the directions that you'll see most likely in circumstances like this. Might say something like this: write the following expressions as simple reduced fractions with no negative exponents. Now, really, it may not say that. It may just say simplify the following. But what they mean by simplifying in this situation is to make each expression simple, reduced, with no negative exponents. And we are going to assume here that all variables represent positive real numbers. Now, what's the significance of that is that we don't have to worry about the cases we've been concerned with all along here, and that's negative bases with even roots, i.e., we can assume that b and x and z here are positive real numbers, and so therefore b to the 1/2 and x to the 1/4 and z to the 1/8, or in general a to 1 over any even integer is going to be a real number. So throughout this exercise set, we can assume we don't have to worry about whether or not we're dealing with real numbers in here or not. So let's look at the first example exercise we've got here. Number 1 says x to the 2/3 times y to the negative 1/4 times x to the 1/2 times y squared. They want us to simplify this to a reduced fraction with no negative exponents. Using the laws of exponents that we know, well, I see that the first and the third factor here are the same powers of the same base, and the second and the fourth are powers of the same base. So let's put those together. You know, we have a terminology. We talk about like terms in algebra, but we don't really talk about like factors, or we don't use that phrase. But in a sense, that's kind of what we're doing here. These are kind of like factors. Factors being multipliers as opposed to terms that are adders. And when we've got the same bases, that is, then we're dealing with the same powers of the same base, and we can use our laws of exponents and combine them in a sense. Using the first law of exponents says that is just one power of x. It is the power of x that's the sum of those two exponents. And the second product here is a power of y. The power of y that's the sum of those two exponents. Nothing new here, really. Same thing we've been doing since we've studied integer exponents. It's just now we've got these rational numbers to contend with. All right, well, we don't want to leave it like that. We need to write this as a reduced fraction, we said. So we need to get a common denominator, which is obviously 6. And so 3 will go into 6 2 times. 2 times 2 is 4. 2 will go into 6 3 times. 3 times 1 is 3. Times, over here, same thing. We need a common denominator. You might want to call this 2 over 1. And the common denominator would be 4. So that'd be a negative 1 plus 8 all over 4. Or this is x to the 7/6 times y to the 7/4. Now, are we done? Well, I said to write it as simple fractions. Now, what does that mean? Remember, simple as opposed to complex. I don't want any denominators or numerators that are fractions. Well, I don't have that. I want it to be simple. I want it to be reduced. That is, I don't want any common factors in numerator and denominator, so we certainly don't have that. And I don't want any negative exponents. And I don't have that. And once you get to there, you're done. That is the final result. Well, let's look at another one. Quite similar. We've got all powers of 6 here. And since they're all powers of 6, we can use the first law of exponents and write that as 6 raised to the sum of those exponents. 2/3 plus a negative 3/4 plus 1/2. And then it's just basic arithmetic. All you got to do is add those fractions together. Well, common denominator, let's change each one of them to 12ths. So this would be 8/12 minus 9/12 plus 6/12. And just add those together. That's 14 minus 9. 14 minus 9 is 5/12. Now, am I going to, you might think, well, are you going to evaluate that? Well, I could try. This is the 12th root of 6 raised to the 5th power. Well, I don't know the number that I have to raise to the 12th power to get 6, so I don't know this quantity, and so I can't raise it to the 5th power. So this is a perfectly good way to describe such a rational power when we don't know it. That's what the notation is for. So you're done. How about the next one over here? Well, again, they're all the same base. Now they're a variable base, and again we can assume that the variable is positive, so these are real numbers. And first thing I could do, I guess, is use the first law of exponents and add the exponents in the numerator, so I could rewrite this as a to the negative 5/3 plus 2/5 over a squared. And again, I need a common denominator. Well, the common denominator here is 15. And so that's, again, I think I'll do it this way. There's the common denominator. 3 will go into 15 5 times, so that's a negative 25 there. 5 will go into 15 3 times. 3 times 2 is 6 over a squared. And add those together, and that would be a to the negative 19/15 over a squared. Not very pretty, is it? And now we subtract, right? Those are 2 powers of a, so you subtract exponents in a situation like that. That would be, let me come over this way a little bit. That would be a to the negative 19/15 minus 2. Using the second law of exponents, just to remind you, a to the m over a to the n is a to the m minus n. That's what I'm doing. This is my m, that's my n. Well, common denominator of 15, and so that's a to the negative 19 minus 30 over 15, or a to the negative 49/15. Well, are we done? Well, no, we said with no negative exponents, so I'd rewrite that as 1 over a to the 49/15. Get rid of that negative exponent. And it's a simple fraction. It's reduced, and it has no negative exponents. And that's it. Okay, here's a couple more. 4 to the 9/4 quantity raised to the negative 2/3. Well, that's just a power of a power, and we know what we do with powers of powers. We multiply the exponents together. So this should equal to then 4 to the 9/4 times a negative 2/3. or 4 to the negative 18/12. And we're sure not going to leave it like that. Remember, we're always going to reduce those rational exponents, so that's, or you could have simplified earlier. I can divide out 6 in both of them, can I? So 6 will go into 18, a negative 3, and 6 will go into there, 2. So it's 4 to the negative 3/2, but hey, that is, got to get rid of the negative exponent, and because my base here is not only a constant, but turns out to be something rather nice, I know how to evaluate that. I can write this as 1 over the second root of 4, which is 2 cubed, or 8. So in simplification situations where you can evaluate, you want to do so, but where it's not convenient or really feasible, then you would leave it in those rational exponents. Okay, what about the next one? 4x cubed to the 1/2 power times 27x squared raised to the negative 1/3 power. Well, I've got a power of a product here, and I've got a power of a product there. So a good rule of thumb in a lot of algebraic situations when you're trying to simplify things, whether you're in an equation or an expression or what, is to remove parentheses to get a better look, you might say. So let's do that here. I'm going to remove the parentheses using laws of exponents, since I know that that's a product, and a power of a product is the product of the powers. I can rewrite that as 4 to the 1/2 times x to the 3 times 1/2, or 3/2, times 27 to the negative 1/3 times x to the 2 times the negative 1/3, or negative 2/3. Well, again, I see here and here the same base, so I know that those powers of x's can be combined, so to speak. So let's put the other two factors in front. 4 to the 1/2 times 27 to the negative 1/3 times x to the 3/2 times x to the negative 2/3. I know you might feel like that's an unnecessary step, and it may be, but just to be clear here, I'm going to write it down. And hey, what about this first factor? 4 to the 1/2? Sure, we can evaluate that. That's 2. And the second factor, well, that's a negative exponent, so I think I'll change it to a positive exponent. And both of these being powers of x, we can add their exponents together. And one more step, 27 to the 1/3, yep, I know that, that's 3. So I have really 1/3, 1 over 3, times 2, times x, adding, changing those both to base, or to denominator 6, would be 9/6 minus 4/6. And finally, 2/3 x to the 9/6 minus 4/6 is 5/6. Now, are we done? Well, it's a simple fraction, no negative exponents, and it's reduced. Let's look at one more of these. Now this one's a little messier looking. 27x cubed y to the 2/3 over 3 to the 4/3 times x to the 5/2 y squared. Well, you might notice that 27 is a perfect cube, isn't it? It's 3 cubed. And that, of course, obviously both of these have the same base, and both of these have the same base, and we can make both of these the same base. So one way to do this one is to make, let's just rewrite that 27 is 3 cubed, and then thinking of it that way, we've got a quotient of 2 powers of 3. What do? We subtract the exponent. So this is 3 to the 3 minus 4/3 times, and we can do the same thing here with the powers of x. X to the 3 minus 5/2 times y to the 2/3 minus 2. Notice it's always, doesn't matter what kind of numbers they are, it's always the numerator's exponent minus the denominator's exponent. And then you just have to live with what kind of exponent you end up with. So let's rewrite this. This is changing to thirds is 9/3 minus 4/3. Changing this to halves, that would be 6/2 minus 5/2. Changing this to thirds, that'd be 2/3 minus 6/3. And now subtract. This would give us 3 to the 5/3 times x to the 1/2 times y to the negative 4/3. We're almost there. We got a negative exponent that we don't want to live with, and everything else is okay. So we can rewrite this as 3 to the 5/3 x to the 1/2 over y to the 4/3, moving the negative exponent into the denominator. Again, there's not any reason to do anything else to this, because again, the root of 3 is not a number that we know. We don't know the number to cube to get 3. So this is a perfectly good way to leave your final result. One last set of problems we want to look at is where you might be asked to simplify, where you have to perform some operations such as multiplying or dividing or such, and with rational exponents involved. Let's look at a couple examples of what I'm talking about here. Perform the indicated operations and simplify. Here we want to square this and add it to the cube root of that. So there's some operations to perform here, and then there's a sum to take if possible. Well, let's take a look at that. So first thing I could do is use the fact that it's a square of a product, so that'd be 4 squared x to the 1/3 times 2, the 2/3 power, plus another power of a product, 27 to the 1/3 x again to the 2 times 1/3 gives me 2/3. 4 squared, yes, is 16x to the 2/3 plus 27 to the 1/3, it's 3x to the 2/3. And we are fortunate to have, what happened is that the two terms that we want to add together turn out to be like terms. Remember, like terms are any terms in which if you ignore the coefficients, they're identical. Well, the coefficient here is 3 and 16. Those are like terms because they have exactly the same variables and exponents. So that's just 19x to the 2/3 as it simplifies. Look at the second problem there. X to the 2/3 times the quantity 3x minus 5. Well, we got to distribute. We got to multiply through. Just happens that we're multiplying through by a rational power of x. I think I'll add maybe an extra step here or two. First thing you might say is that that's x to the 2/3 times 3x minus x to the 2/3 times 5. I've just distributed. But x, of course, is understood to be of exponent 1, and so there you have two powers of x, same basis, so law of exponents tells us that we can combine those together as x to the 2/3 plus 1. Well, 1 is 3/3. Can we do all that together? That's 2/3 plus 3/3 is 5/3 minus 5. Always put the coefficients in front of the term. 5x to the 2/3. Now, can we go any further? No. Be very, very cautious in dealing with sums and differences of powers of variables. There's not many things we know about them, and that is as far as you can go. They're not like terms, so that's simplified. Okay, how about this one? Well, just really more of the same thing. It's a monomial, if you will, a one-term expression anyway, multiplied times a three-term expression. We might call kind of a trinomial. And we do the same thing. We distribute. Let's see how this turns out. So first I'd multiply 2 times 3 and I'd get 6. Here's x to the 1/2 times x to the 1/2. Well, that's x to the 1/2 plus 1/2 because those are the same bases, minus over here 2 times a negative, or -1 is a -2. X to the 1/2 times x, we just did that, that's x to the, or something like that. X to the 1/2 times x to the 1 is x to the 1/2 plus 1 times y plus, over here there's nothing we can really do but just show the product, 2x to the 1/2 y to the 1/2. And then a little simplifying, this is 2x to the 1, or just, 6x to the 1, or just 6x, minus 2x to the 3/2 y plus 2x to the 1/2 y to the 1/2. And that's about all we can do with that. One more here. We've got two binomial expressions that we want to multiply together. Well, we kind of have to, again, distribute our kind of a foiling pattern. The first together, the inner two, the outer two, and the last two, right? And let's see what we get. X to the 1/3 times x to the 1/2. Well, that's x to the 1/3 plus 1/2. Now the inner two, maybe. that'd be plus 2x to the 1/2. The outer 2, that'd be plus a negative, wouldn't it? X to the 1/3. And then minus 2. Simplify that. 1/2 plus 1/3. Well, we know what that is. That's 2/6 plus 3/6, which is 5/6, plus 2x to the 1/2 minus x to the 1/3 minus 2. Quite often in multiplying expressions like this together, things don't work out very nicely. That's about all you'll end up with is distinct terms. Well, we've covered quite a bit of territory here. You should have enough examples to go through the problems in your text over this topic of rational exponents. The second half of this topic is dealing with an alternate way of writing rational exponents or rational powers of a number, using, rather than exponential notation, using something called radical notation. And that will be on a separate tape to follow this one. Be sure that you have a good background, a good understanding of the exponential notation before you start the second tape, because I'll be assuming the information from this one. So you may want to revisit some of these topics that we've covered on this tape another time at a little more in depth before you go on to the next tape.